Okay, so when last we left off, we were looking at approximating area. So figuring out the area under the curve between the x-axis and a particular graph. So in a very rough way, we can draw these rectangles, and that gives us a rough idea of the area. And then we did one example where we took the left endpoints and actually figured out it was a third plus a fourth plus a fifth, which is 12/60ths. Or 1/15th, I guess. Meh. But when we look at this graph, we can see that using the left endpoints, because this was a decreasing graph, that our area is bigger than 1/15. All of our rectangles were larger than the area under the curve. So that's actually giving us an upper bound. We know for sure the area can't be bigger than 1/15. Now, if we do the same idea, but we look at the right endpoints, so I've got my same interval with my rectangles. We got our endpoints, all four of them filled in. So the left, the two middle, and the right endpoints written in thirds, just so it's easy to see that they're evenly split. Yeah, and we're doing the right side. So when I look at each of these rectangles, I have the base, and then I have the height. So my height is determined by the function value. I'm just going to put f of number, because what number we put in there depends on whether we're looking at the left or the right endpoint or something else. There's a number of ways to actually approximate the area. Usually we use rectangles though, because the area of them is nice and easy to work with. We just, the width times the height. So 4/3 is the width of each of these rectangles because we deliberately made them the same width. And we're doing that on purpose because later on we can vary that width. We're going to make it skinnier and skinnier. So we're keeping the width equal on purpose. So now we just have to do the function values for the heights. And since we're using right endpoints, we actually do label all of these x values. So, I mean, the 12/3 is really 4. We call that x sub 0 because it's like our origin, our starting point. Then x1, x2, and x3. So we have 3 rectangles, and x sub 3 is our third endpoint. So we're going to plug in. So we'll keep our 4/3 for the width of all of the rectangles. All right. So x sub 1 is 16/3 plus x sub 2 is 20/3 plus f of x sub 3 is 24/3, which I'll just write the 8. All right, now we're just going to plug in what those function values are. So remember, our function is 1 over x. So f of 16/3 is 1 over 16/3. Plus f of 20/3 is 1 over 20/3. Plus f of 8 is 1 over 8. And why do math by hand when you have a calculator? 4 divided by 3 times 3 divided by 16 plus 3 divided by 20 plus 1 divided by 8. And 37/60. So that's 0.616 repeating. I did my math wrong earlier. This was not that. So we've got 0.78 as an upward bound, and then 0.616 as a lower bound. So the actual area under the curve is between those two numbers. Now, another approximation we can do is the midpoint between each of those numbers, which involves calculating third, like other function values to represent them. And the midpoint does, for the most part, seem to give us a better approximation. All right, so because it gives us a little bit of over and under. But when we do the midpoint, it's not actually going to be x sub 1, x sub, like the values, the function values are a little bit different. So between 12/3 and 16/3, halfway between those is 14/3. And then halfway between 16 and 20 is 18/3, which does actually reduce to 6. And then halfway in between the 20 and the 24 is 22/3. So those are the three x values we're going to use. So it's still our same rectangle width. We're just picking slightly different function values. Now I'm just going to crunch that up on the calculator just so we see the comparison of the numbers. So 4 divided by 3 times, open parentheses, 3/14 plus 3/18 plus 3/22. So 0.68. Ew, is ugly fraction. 478 over 693, which is approximately 0.6897. So pretty close to 0.69. It's not quite halfway in between the numbers, but pretty close. So similar to what we were just looking at. So this one, it's asking what kind of Riemann sum. This is asking, is it a left or a right endpoint? So when we look at the rectangles, the height of the rectangle is determined by the numbers on the left. That's where the function value is. And then based on the picture, this is an under approximation. So it's not that left endpoints are always an under approximation, but if the graph is strictly increasing over the interval we're looking at, then a left approximation will be a left Riemann sum will be an under approximation of the area. Now down here, same graph, but now I'm looking at a right Riemann sum. And it's an over approximation. So, like finding these arbitrary rectangles and figuring out those areas and then like trying to figure out is that bigger or smaller, especially when the curve is not strictly increasing or decreasing, when it's like doing all sorts of crazy things, like this gets ridiculous. So we're going to use sigma, which unfortunately means we need to review sigma notation. And it can feel like, oh my God, when are we ever going to use this again? At the end of Cal 2. Sigma notation itself, though, is very similar to the way like computer programming and loop notation works. Because you're saying do this thing over and over again a certain number of times. And in this case with sigma, it's always and add all those results. So when we're doing 1 plus 2 all the way up to plus 10, like in words, we're saying add the first 10 integers. So the sigma notation is another way to write this. So when we write our big sigma, we're going to have a variable that we're going to write a formula in terms of. We typically use k, but sometimes we'll use I. Either of those letters tend to show up in programming when you're doing loops. So k equals, and then you pick a starting index. Usually you pick 1, but sometimes you can pick 0. The final index is how many times you're going to do the formula. And then a of k says a function depending on the index. So this is written in terms of k. Now, there may be other variables inside the formula. We're going to see that towards the end of class today. But the only variable that has like meaning to the sigma notation is the k. Any other variable is just going to keep showing up as that variable when we're doing the formula. The only thing that changes is the k's. So are adding the first 10 integers. So using our sigma notation, I'm going to start at 1, and I'm going to go to 10. And then what I want inside the sigma, the formula, is whatever produces each of these terms I'm adding. In this case, the terms are literally just the number that like I'm indexing. So when k equals 1, I'll put 1. Then sigma notation means put plus. Then I increment my index. Now k is 2. I put it in the formula. I get 2. I write my 2 down. Plus. Then I increment 3. I write my 3 down. So this is another way of saying the same thing as adding all the integers from 1 to 10. Now, it can seem a little bit extra to go to this, but what if instead of adding the first 10 integers, I was adding the first 100 integers? You don't want to sit there and have to write all 100 integers, but all I would have to change for the formula is just turn that into 100, and there it is. So a little bit extra practice with sigma notation. We're not going to actually come up with the result. We're just going to write what the initial sum would be. So this sigma notation starts from k equals 2 and goes to 6. And my formula is 1 over k. So I start with 2. I plug in 2 to my formula. So I get 1 over 2. And then sigma always means plus. Now I plug in my next number, 3. So now I have plus a third, plus my next number is a fourth, plus a fifth, plus a sixth, plus, oh wait, 6 is where we're stopping. So done. Now, certainly I could punch that on the calculator and add it up. Not the point here, though. The point is just to understand the way the notation works. So when I have the sum of k equals 0 to 6, now my formula is a little more interesting. It's 2 to the k. So I plug in my first k number, which is 0. So my first term is going to be 2 to the 0. Plus. Now I'll have 2 to the first power, plus 2 to the second power, plus 2 to the third, plus, this gets tedious to write. So we started at 0, we indexed all the way up to 6. So we wrote 7 powers of 2. The 0th power all the way up to the 6th power. So there's 7 terms in that summation. Now, sometimes the sigma notation doesn't have k inside where the formula goes. It's just a number. So I start with k equals 1. I plug it into my formula in quotes. There's nowhere to put the k, but my formula says put 1/6. All right. So I have 1/6 plus, now I index. So I've done k equals 1. Now I'm doing k equals 2. I put another 6th. Now I'm doing k equals 3. I put another 6th. K equals 4. I put another 6th. Plus 5th term plus 6th term. So going from k equals 1 to 6 of the formula 1/6, I am adding 1/6 6 times because there's 6 terms, 6 indexes in my summation. So this ends up being 6 times 1/6. So when it's just saying do the summation formula for a constant, you just end up with however many copies of the constant there are for indices in the summation. And usually that number of copies ends up being the number on top of the summation. As long as we're starting at k=1, then I get 6 terms. So typically when we look at sigma notation, typically we're going to go out of our way to try to start at 1. So questions on the way, like the quick rules of the way sigma notation works. All right. So sigma notation has some nice properties, and they're very similar to the properties that we get from derivatives and that we also get with our integrals. So if I have the summation of a constant, the example we just saw with the 1/6, and I'm doing my summation from 1 to n, then I just get n times the constant for the result of that sigma notation. So I had ugly sigma notation. I say ugly just because there's a whole lot going on there. And I get it to equal just a nice simple formula. If I have a constant, then I can factor that constant out because the summation is just a whole bunch of numbers being added. And if all of the numbers are being multiplied by a constant, I could write the constant for every term, or I can factor it out as a common factor. If I have the summation of 2 terms being added, I can split the summation across the terms. Likewise, if I have 2 terms being subtracted, I can split the summation across the subtraction. Now, this last rule is a little bit weird. So we're starting a summation from 1 to n. I can split the summation from 1 to some other number m, and then from m plus 1 to the end number n. So basically, instead of doing the sum of the first 10 integers, I could write it as the sum from 1 to 5 plus the sum from 6 to 10. So I'm just taking the same list of indices and just splitting it between 2 summations. Usually we don't bother too much with this, but if I have a summation that starts at 0, I can split off the first term of the summation and then rewrite the rest of it from 1 to my end number, because most of my formulas, like all the formulas here, are written from 1 to n. So we are going to be kind of stuck with wanting to see 1 to n. So in the rare instance where we start at a 0, we can split the indices like this. So it turns out when I look at the sum of particular things, so in this case, this is the sum from I equals 1 to n of I. Or it could be k equals 1 to n of k. Like I said, we switch between I and k for the indices. So I'm adding all the numbers from 1 to n. It turns out that that list is always n times the next integer, n plus 1, all divided by 2. So if I think of Like one of the ways we usually discuss this summation is I added everything from 1 to n. Well, what if I also put everything from n down to 1 and added that as well? As weird as that sounds. Then I have pairs of terms, n plus 1, n minus 1 plus 2 is the same as n plus 1, and then n plus 1 plus n is n plus 1. So I've added, like I doubled the list because I added the list to itself again. But now I rewrote it as pairs, where each of my pairs is the sum n plus 1. The number of pairs, there are n pairs of the sum n plus 1. But because I added the thing to itself, if I divide that result by 2, that'll give me this total summation of one of the lists. So there is like a logic to the way that formula works. So theoretically, there is a logic to the way the other two formulas work, but I don't have an easy explanation for those. So generally, it's just if I'm adding a bunch of squared terms, I get this crazy thing. If I'm adding a bunch of cubed terms, strangely enough, I get the result from the first thing squared. I'm sure there's some pretty explanation for why that's the case, but we end up with these 3 formulas. You are not going to need to know these formulas on the final, but in some advanced math classes where we make you play with a lot of sigma notation, you do end up using these formulas enough that you would memorize them. Just because you reference them so much, you get used to it. So if I'm looking at this guy here, the sum from k equals 1 to 11 of 9k cubed. Well, that 9 is a constant. So I'm going to pull that out of my sigma. So now I have 9 times the summation from 1 to 11 of k cubed. And I look, my formula here tells me if I'm doing the summation from 1 to n of I cubed, then that summation equals this formula where the n shows up in my formula here. Notice the i's that I had don't show up in the formula at all. So it just turns out if I add the first 11 cubes, I can use this formula as a shortcut for what that end result is going to be. So I still have my 9 times, but now I'm going to use my formula. So my n value is the 11. So I'm going to have 11 squared times 11 plus 1 squared all over 4. So 11 squared is 121. 11 plus 1 is 12. 12 squared is 144. And then we divide that by 4. So 121 times 144 divided by 4. So we get 9 times 4,356. So it turns out if I add the first 11 cubes, I get 4,356. And then I just multiply that by 9 and I get a ridiculous number, 39,204. Cool. So instead of manually adding the first 11 cubes, I used a shortcut formula, and then I multiplied the result by 9 because my formula had a 9 being multiplied to all of those cubes. So there is a way to take a weird sigma notation with a formula in terms of a constant times the index squared or the index cubed. So I can have a constant k squared or k cubed. There's a formula that I can substitute out for that. All right. So this particular crazy nonsense, I have n values in here. And the only reason we are doing this is because we are literally going to see this in the next problem when we apply this concept back to our rectangles under the curve. All right, so my sigma, I have subtraction. So I'm going to split my sigma between the subtraction. So I will have the sum from k equals 1 to n of 5k over n squared minus the sum from k equals 1 to n of 8 over n. All right, now when I look at my sigmas, my index is in terms of the variable k. Anything that is not k is considered a constant for the purposes of the summation, because I'm going to do whatever I do with my k, and then I'll just multiply it by whatever the non-k portions are if they're being multiplied and divided. So the 5 over n squared is considered a constant. So I can pull that outside of the summation. And then the 8 over n, there is no k there. So that is considered a constant. But when I have pulled the entirety out of my formula, I need a 1 as a placeholder. Because I am still supposed to be adding that 8 over n times. So I have my 5 over n squared. Now my sum from 1 to n of k ends up being our shortcut formula over here. N times n plus 1 divided by 2. Minus, then I have my 8 over n. And then my sum from 1 to n of the number 1, I'm just adding 1 n times, so I get an n there. Go for it. To the 8 over n? Yeah. So it's 8 over n times. So now I have 8 over n times n, or I could write it n times 8 over n. Now, if we start cleaning this up, this 8 over n times n is actually just 8. I mean, minus 8. And then my 5 over n squared times, this ends up being n squared plus n all over 2. I'm going to rearrange this a little more interesting. I'm going to move this entire result over. So the n squared and the 2, like this is fractions. So the 5 and the 2 are just literal numbers. The n squared with the n squared plus n on top. I move those together because now this internal fraction here, I can actually like simplify it. So we'll have the 5 halves times, I would have 1 plus 1 over n, and then the minus 8. And believe it or not, all of that is just algebra. Like in a full, like given a whole lot of time, sigma notation is very commonly supposed to be covered at the end of like algebra 2 in high school, somewhere in there. Maybe sometimes a little bit in geometry, but usually at the end of algebra 2, sometimes in pre-calculus. But with the way the federal government is gone, like so many things that were deemed extra just got stripped from curriculums. So if you've never really seen sigma notation before, I can't say I'm surprised. Now, the only reason I went those extra steps is because we're going to see, I'm going to apply the limit as n goes to infinity to this. And if I do it to this end result here, the limit will actually work. Like I can actually apply it and get an end result and not just a weird infinity. So when I do the limit as n goes to infinity of 1 over n, 1 over infinity goes to 0. So I end up with 1 plus 0. Well, that's just 1 times 5 halves. So I actually end up with 5 halves minus 8, which is negative 11 halves. So even though we started with this really crazy formula from 1 to n, adding and subtracting a whole bunch of things, and then I do the limit as n goes to infinity, apparently, if I make n just increase, 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 this whole ridiculous sum difference formula will end up equaling negative 11 halves. So I guess the negative 8 over n was a little bit stronger than the 5k over n squared piece. Or I guess a little bit bigger, maybe. So weird, crazy algebra with one calculus step at the end. So now back to our calculus. So my Riemann sum is just a fancy way of saying do the rectangle approximation for the area under the curve. So we can use sigma notation to do this. So just in a very generic sense, from k equals 1 to 3, I've got the width times the height for each rectangle. So just in a very generic sense, I can use my sigma notation to say add those 3 rectangles. But now we're going to make it a little more interesting. We're going to get a little fancier with our formula. So what if instead of focusing on 3 rectangles, well, what if I said, I don't know how many rectangles I want. I just want to write this formula in a general sense. So n represents our number of rectangles. That n shows up as our end n for the summation indices. Sigma notation is just saying add all the things. Delta X is our base, or what I was calling the width. But when we're making these rectangles, the base, the width, is always the same. And that distance always ends up being the distance between two x values. So I called that first one x sub 0, x sub 1, x sub 2, x sub 3. So that width is x1 minus x0, or x2 minus x1, or x3 minus x2. But it is a change in the x values. So that's why we're using that delta x in the formula. Just a mathematical notation for saying change in a thing. Our index is only showing up in the heights. And it's showing up in whatever variable, like whether we're picking the left end point or the right end point or the midpoint, like whichever function value we pick to determine the height, we're going to label our x values based on that index. And then we plug that into the function formula. Now, our delta x formula, if instead of doing 3 rectangles, I don't know how many rectangles I'm doing, I'd take the full distance between the x's, so when we're doing the area under a curve, A and B are the start and the end value for the x's. So A is always x sub 0, B is always x sub n. So if I take the full distance between all of those x values and divide it by how many partitions I want, how many rectangles, that'll give me the width of one rectangle. So our delta x always ends up with this formula, b minus a divided by n. So that formula is going to kind of like poof, show up out of the blue, especially if you look in the book. But that's because we're doing like, if I was going to subdivide it into 10 rectangles and I was looking at, this was, it didn't even pick pretty numbers. Earlier, we were doing from 4 to 6. So I would do 6, my end number, minus 4, my beginning number, which is a distance of 2. And then I divide that by 10 rectangles. So each rectangle will have a width of 1/5 of a unit, 2 over 10, which is 1 over 5. If I wanted 100 rectangles, it'd still be the b minus a, 6 minus 4, but I'd be dividing by 100. And then I'd be taking 100 different x values and plugging it into a function, and it gets tedious. This is where the shortcut formulas really come into play. So if I am doing a right endpoint approximation, then A is my x sub 0 point. Then my first right endpoint is x sub 1. So my first height would be f of x sub 1. So my index here starts at 1 and goes to n. So we see it up here. They've like written it out in a dot, dot, dot formula. So the function value on the right times the width, the function value on the right of the next rectangle times the width, on and on and on. And then they just took those x sub 1, x sub 2, x sub n, and turned it into an x sub I formula running from I equals 1 to n. Apparently we have a fancy notation. R sub n is a right endpoint approximation. But it's just doing the same thing we did before. We're just taking the similar, like identical widths of all of the rectangles times the changing heights of all of the rectangles, and then adding those results. Now, if I do a left approximation, my indices change a little. So it goes from 0 to n minus 1. So I could write my sigma notation from I equals 0 and end at n minus 1. And then this would be f of x sub I. So let me just write that just so we're clear. Like I could also say this. And this might help or just might make it more confusing. So I started with x sub 0. I ended with x sub n minus 1. Because I'm not going to use my very right endpoint because I'm doing the left endpoints. So the very last rectangle, I use the one on the left, and then I don't use the last x. But when I write my notation this way, I'm running from 0 to n minus 1. All of our formulas that we used earlier started at 1. So there is a way to rewrite this formula. So I change my indices to run from 1 to n, and I just change where the index is being referenced in the formula, and I basically move the minus 1 into the formula. But again, you're not going to have to memorize these formulas. We're going to give you guys like a very basic approximation with a finite number of rectangles, and you can just literally crunch it out by hand. So when we look at our approximation, when I have 3 rectangles, it's a pretty crappy approximation. So what do I want to do to get a better approximation? Yep. Make smaller and smaller width rectangles, which means I'm making more and more rectangles. So if I make the number of rectangles, which was n in our formula, n represents the number of rectangles. If I make n go to infinity, that is going to give me the actual result. So the area under the curve of a function on a particular interval from a to b. And when we say the area under the curve, technically what we mean here is the area between the curve and the x-axis. It's just the x-axis, the flat line, is the line y equals 0. So I'm looking at the difference between my curve and 0. So if I subtract 0, that doesn't change the result. So when we say the area under the curve, the implied other boundary is always the x-axis. So we do our summation, and then we just let the number of rectangles go to infinity. And it seems like this would make the end result quite ridiculous. But we'll actually get finite formulas that we can use for the approximations. So our first step, the delta x, is b minus a over n. Now our n is going to stay n because eventually we're going to do the limit as n goes to infinity. But the b and a, they gave us the interval from 0 to 2. So that is 2 minus 0. So this is the width of the rectangles. Now, if I start looking at my first x values, so when we write the x sub 1, x sub 2, x sub 3 here, I like to do this like using a number line. So my ax value, which is x sub 0, in this case is the number 0. And then eventually my b value is 2. But when I'm going to go to that first x value, or the next x value, and on and on and on, and this is supposed to be like dot, 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 meaning there's a whole bunch of x's in there. I get to my first x value by starting from 0 and adding my width, 2 over n. My second x value is the previous x value plus the width again. My third x value is the previous x value plus another width, another increment over. Whoa. Now I can simplify these formulas down. So it turns out my x sub 1 is just 2 over n. My x sub 2, I end up with 2 copies of 2 over n. My x sub 3, I end up with 3 copies of 2 over n. So now, using those x values, I want to figure out what's a formula for an arbitrary x value, an x sub k. So if I'm going like 7 x values in, what would be my formula for the 7th x value? 7 times what? Yes, we can. But we need to know what we're writing in the sigma notation, so that's why we're slowing it down so much. If your brain is like already jumping ahead, that's okay. So our x sub k formula, I'm going to have my 2 over n times k, where k is how many widths over I'm going for that particular x value. So our delta x value always ends up being included in our x sub k value. Sometimes, though, there's going to be a number in front. This interval, though, our a value was 0. So that 0 plus that we had, like, just ended up dropping off because it was the number 0. So now our f of x sub k literally means plug the x sub k formula into our function. So f of, we can write that as 2k over n. And now we're actually going to plug it into the formula. So 7 times 2k over n squared plus 9. Yuck. So this will be 4k squared times 7 will be 28k squared over n squared plus 9. That is what f of x sub k is. So this is our height. So now we've got the area of one rectangle. The width times the height. So our height is that weird formula we just got, 28k squared over n squared plus 9 times our width was 2 over n. So that is what's going to go inside our sigma notation. That's the area of one rectangle. Now we're going to write it with sigma. So we have the sum from k equals 1 to n of 28 k squared over n squared plus 9 times 2 over n. Now, before we work out the limit, we're actually supposed to use one of our fancy formulas to get the sigma to go away. Okay, so this is going to look a little weird. The 2 over n doesn't have a k in it, so that is a constant I can pull outside of my sigma. Now I have sigma split with a sum. I can split the sigma across the sum. I still have the 2 over n outside. And now I'm putting some brackets because now I'm splitting that sigma. Now my 28 over n squared does not involve a k, so that can come outside of that front sigma. I still have the 2 over n out front. And it's very easy to forget that 2 over n. So the 28 over n squared comes outside that sigma. So it's from k equals 1 to n of just k squared. Now we'll be able to fill in from our formula. But I'm going to finish writing my line. Hold on, let me make that green. Now our sum from k equals 1 to n of 9, I'm just doing 9 plus 9 plus 9 n times. So that sigma notation, I can just go ahead and fill in with the formula I know. And now I'm going to do the same thing for the k squared. So I still have my 2 over n, my bracket, then the 28 over n squared times, then my formula for the k squared is n times n plus 1 times 2n plus 1 all over 6. And then plus 9n. Now, in order to be able to do the limit as n goes to infinity, at the very least, I need to distribute this 2 over n through. So that is into this first crazy product and over here times the 9n. So 28 times 2 is 56. So I have 56 over n cubed times the n times n plus 1 times 2n plus 1 all over 6. So give me a second. So we will have 2n cubed plus 3n squared plus 1n. And then 2 over n times 9n, 2 times 9 is 18. Over n times n, the n's cancel, so we just get a plus 18 at the end. Now, in order to start getting ready to do the limit, I'm going to swap my 6 and my n cubed, and then I'm going to split the n cubed into each of those terms on top. So I'm going to have 56 over 6 times, it'll be like 2n cubed over n cubed plus 3n squared over n cubed plus n over n cubed, and then the plus 18 still. So we end up with 56 over 6 times 2 plus 3 over n plus 1 over n squared plus 18. Now, when I apply the limit as n goes to infinity of this result, my 3 over n and my 1 over n squared, both of those will go to 0. So I'm going to end up with 56 over 6 times 2 plus 18, which, equals some magic. $110 over 3, which is 36.6 repeating. So that is a giant, disgusting mess. So remember way back for exam 1, we learned about the long definition of the derivative, right? So the limit of f of x plus h minus f of x all over h And we learned about the algebra hell of trying to simplify that fraction. And then we learned the power rule and we were like, why, Dr. Liz? Why did you make us do that horrible mess? So you could appreciate the beauty of the closed formulas. So I present to you second case. Here is the disgusting mess that is doing integration the long way. So appreciate how horrific it is. And then we actually already learned some of the shortcuts. Area under the curve, turns out, is the integral from A to B. So we're going to define what a definite integral is when we have bounds, but the antiderivative is the integral, which is the area under the curve. So it turns out all these weird things that seemed very separate actually all coalesce to be the same idea. So it can feel like, oh, we're done for the day. No, technically we're supposed to get through the next section as well. So 5.2 is the actual definite integral. So when we learned about the indefinite integral, it's the most general antiderivative of f, written as capital F of x, and then we have our arbitrary constant plus c. Then we learned about the limit as n goes to infinity of the Riemann sum. So here's how the two things equal. So the Riemann sum had bounds. We had from A to B area under the curve. And it turns out if I do all of that crazy algebra I just did, the limit as n goes to infinity of the arbitrary Riemann sum, I will get the same formula as the antiderivative of the function. It does have a caveat, provided the limit exists. So if this limit exists, the function f of x is said to be integrable on a to b, or is an integrable function. So if we put bounds on the top and the bottom, if we say just focusing on from a to b, I get the area under the curve. Now, this ends up with some weird caveats. So if I look at the integral from starting at A and ending at A, that's the same number. So I haven't actually moved anywhere. My delta x is 0. So the area under the curve at a singular number is 0. Now, if I'm looking at an integral and my bounds are backwards, like notice the first one is from B to A. I can flip the bounds, but I just have to put a negative sign. So our fancy integral here is just a summation. It's a weird encoded sigma notation. So all of the rules that we got for free with sigma notation that we saw before worked with indefinite integrals work on definite integrals. So we saw with the summation what Christy termed splitting the deck. So I have my A versus my B. I can split my integral and just put some extra number in between them if I want. We very rarely do that, but eventually in the middle of Cal 2, you'll actually see integrals at infinity. And sometimes we need a number in between, so we're not looking at two limits of infinity. Or if my function formula changes, because I have a piecewise function. So if I'm like from 1 to 2, here's one formula, and then from 2 to 7, here's this other formula. If I'm looking at the area under the curve, I can write the area under f of x from 1 to 7, but if I'm actually going to evaluate it, I need to write the individual formulas for when the formulas are true. So I can use my split the deck to split the bounds, so I can use my appropriate formulas for the values they're true for. All right, so we do have a web work question that asks this. It's in this weird format. So you really got to pay attention to the bounds here. So this first one, the integral from 12 to 12 of something. What happens when the bounds are the same? Yep, we get a big fat goose egg. Because we're starting at 12 and ending at 12, so there is no delta x. So the area under the curve at a number is always 0. All right, so now my next one is going kind of backwards, 17 to 11. And then my function is g of x. So I look up here, well, here's my g of x. But my bounds there are from 11 to 17. Like the order is backwards, so I can use my bound flipping rule. So it's the negative of the integral from 11 to 17 of g of x dx. And now I know what that integral equals. This whole thing is the same as negative 23. So this whole thing is the same as negative 23, but I had a negative in front. So the end result here is positive 23. Now my 11 to 12 of 6 times f of x, well, the constant just gets pulled out front. So this is 6 times the integral from 11 to 12 of f of x dx. And then 11 to 12 of f of x dx is the same as negative 3. So 6 times negative 3 gives us negative 18. Now, somewhere in here, I usually get, how do we get a negative area under a curve? Like, I know when I first learned about integrals, that was definitely a thought I had. I was like, how does this make any sense for the area being negative? So if I'm looking at, let's say that stretch there. So this curve is below the x-axis. So all of my function values here are negative. And remember, when we did the Riemann sum, the function values were the heights of the rectangle. So if those function values are negative, then the heights of the rectangle are negative. And when we do a negative number times the positive width, it's still negative. So all getting a negative area result means is that the function is beneath the x-axis. Now, if I was actually like, going to map this as like some weird rug that I made in a funky shape, then the absolute value of it, that would be the area of the rug. because I could like flip the entire function by multiplying by a -1, and that would turn the entire area positive. This does mean, though, sometimes when you're looking at an area and part of the graph is above the axis and part of the graph is below the axis, you'll actually get some cancellation of areas. So if you truly want to know the actual area instead of just what the total summation is, sometimes you actually need to look at the graph and sort out where is this area going to evaluate as negative and where is the area going to evaluate as positive, and you split them apart and make sure to change the signs appropriately. It just depends on the context of the problem you're doing. Most of the problems were just like, here's how to do an integral, and we don't think too much about this context. All right. So I'm going to leave the rest of those for next time, I think. Yeah, we'll leave it for next time. And then next time, if I need to, I'll do an extra recording to catch us up so we still have one day for review.